My name is Dalia Al-Swatli, and I'm an engineer with a master's degree in advanced architecture. Today, I will be discussing with you my latest research, which was upon a comprehensive evaluation of thermal performance and time lag in residential buildings or residential apartments, a numerical simulation study on phase change material and Mycelium integration in Amman. This conference, I will be discussing the introduction, methodology, results, and discussion, then wrapping it up with my conclusions and recommendations on this research. Starting with the introduction, I will be dividing my title into three parts and discussing each part alone and the specificity of each term in each part. Starting up with the first part of the title is a comprehensive evaluation of thermal performance and time lag in residential apartments. Why did I choose the specificity of thermal performance? Because, as I said in the title, that this research was held in Amman, and Amman is the capital of Jordan. Jordan is a country in the Middle East that has multiple advantages to live in, but one of its disadvantages that it lacks energy sources, especially non-renewable energy sources. And as seen in this illustration that I have done, that throughout the years from 2016 to 2020, and as predicted in 2025, that most reliance on energy consumption was on crude oil and its products. The crude oil is one of the non-renewable energy sources that here in Jordan we actually import from our Arab countries or nearby Arab countries, which means that we have actually a very huge problem since the most reliance was on crude oil and it's an imported energy source. Maybe some of you now are thinking about why don't we use the renewable energy sources since it's everywhere and it surrounds us, such as solar energy, windmills, and other stuff, because each energy source needs its own tools, and yet we haven't implemented the tools yet here in Jordan. Starting out with my title, I will be dividing it into three parts, as I said. The second part of the title is in residential apartments. Why did I choose the sector of residential apartments? Because as illustrated here, that we have four main sectors in energy consumption. The first one is transportation, ranking first with 48% of energy consumption. Then what comes second is residential and public apartments, which means that the residential apartments actually do consume about 20%. It ranks second in most sector here in Jordan on reliance on non-renewable energy sources and in consumption of it. The third and last part of the title is a study on phase change material with mycelium integration. This material is what I studied in this research, and it was what I thought of it as a solution of the problem that I mentioned before. What was the problem actually? The problem is that there's an increased demand on heating and cooling systems here in Jordan in the residential apartments and residential buildings, which means that there is an efficient problem with the thermal insulation. Starting with the material, the phase change material mycelium integration, it's actually a combination of two materials. The first material is phase change material. What is phase change material? Phase change material is material, it's actually a self-explanatory material because it changes its phase. It's a material that changes its phase when it is exposed to heat from solid to liquid, and when the heat drops below a certain degree, it actually releases the heat that it consumed it, and then turning its phase back to solid. How would I be using it in the residential apartments or residential building? It will be a layer between the layers of the residential envelope. What will be the envelope that I will be studying? It was the ground floor slab, the exterior walls, and the roof of the last level of the residential apartment. It's actually a specific envelope of the residential building. The phase change material will be a layer that will be implemented between the other layers in the envelope. How would it work? When the phase change material or the envelope of the building is exposed to 25 degrees Celsius of heat or even more, The material, phase change material, will keep on absorbing the heat, decreasing its entrance into the enclosure, saving the enclosure's a perfect temperature and perfect environment. And then when it absorbs the heat by default, such as an ice cube, it will change its phase from solid to liquid. And then when the exterior temperature drops actually under or beneath 25 degrees Celsius, the material itself, the phase change material, will start to solidify, which means it will start to change its phase from liquid to solid. And while doing that, it will have a heat release heat release into the interior, saving the interior's temperature and keeping it into the comfortable temperature in the enclosure when the outdoor temperatures are below a certain degree, which means that the outdoor temperature is actually a bit chilly. Here's an illustration showing how phase change material will change its phase back to solid while it releases its heat into the interior. The second material of the combination of phase change material mycelium integration is mycelium. Why did I choose this specific material? What is mycelium? Mycelium is this actually deciduous fungi or fungus. It's a material that actually surrounds us everywhere. You can find it everywhere. Multiple researches have been done on this material, mycelium, in architecture, and most of them actually have said that recommended to study this specific material with phase change material, and this is what I've done here. Mycelium actually boosts the thermal performance of phase change material and boosts its thermal booster for the phase change material as an insulation or as a booster, as I said before. So here comes the phase change material in a very general way and with mycelium integration, as I have said. Again, I will repeat that the envelope that I will be studying here is the roof, the ground floor slab of the residential apartment, and the exterior walls of the residential building. Just to wrap stuff up, what is my main problem here? That here the residential buildings here in Jordan actually have heat gain in summer, which means that we need to power the AC and the air conditioning and using more electricity just to cool the enclosure in the summer, while in winter there is heat loss, which means that the building itself isn't helping itself. We try to heat it, but the heat escapes somehow. And my solution was to turn the residential building in what is called a thermal mass. What is a thermal mass? Thermal mass is that the building itself or the residential apartment will be able to cool itself by its own, to heat itself by its own, and that's what the phase change material, the mycelium integration, will do by implementing it as a layer in the envelope, which means that in the daytime there's heat absorption, decreasing the amount of heat entering the enclosure and decreasing by default the amount of energy that we will use to cool the enclosure. While in nighttime or in colder days, the phase change material will release the heat that it absorbed before or later on, before. Releasing it in the enclosure and decreasing the amount of heat or energy that we need to heat the interior. Here's an illustration showing two methods, two buildings, one without the PCMMI, one with it. You can see that without the PCMMI, that doesn't have the outline of red outline, we can see that you can feel the spectrum of the temperature throughout the 24 hours of the day, while with the PCMMI, you can see that it is saved into a comfortable temperature, only between 19 to 21 or 22 degrees Celsius. Now I know that there's this blink or this question that's popping up. You know, the phase change material is a material that changes its phase into liquid at some point. How wouldn't it leak into the interior? That's by using microencapsulation. Microencapsulation is a type of rolls that are used only for the phase change material mycelium integration or bio PCM, and that's by putting the mixture into these encapsules, and then they will be closed, which means that it will expand and shrink into these encapsules without and preventing its leakage into the interior. PCMMI in Jordan, we can find it in the eastern side of the Dead Sea because it's a type of the salts, because I've studied the organic PCMMI. The research hypothesis and the research questions and the research objectives will be achieved and answered throughout the methodology now. The second part of this conference will be the methodology. I've conducted two methodologies throughout this research. The first one is a numerical simulation. The second one is parametric analysis. In order to achieve my objective, which is making a simulation of the residential building in Amman and evaluating its thermal performance, I need to make a simulation, because how would I understand, how would the PCMMI work? Because we actually don't use it here in Amman, but we could. But how would I know its performance? That's by just simulating it, doing a simulation of it. So in order to understand how to make a simulation for it, I needed to understand what is my main variable to choose the residential apartment that I will be simulating it, because I needed something that's actually constructed on real life. So I've divided, throughout the references, I've seen that Jordan has three main climatic zones, and the first one is Badia and desert, which is number 3 here in the right side of the slide. We can see that the middle side, which is number 2, is the highlands, and the lowlands is the number 1, which is on the left side. What I chose a residential apartment in Amman, which is the capital, in the climatic zone of highlands, which means that the results of this research could be validated and generalized on residential buildings type residential apartments on a highlands climatic zone in Jordan. I've chosen a residential apartment in Khalda, which is a neighborhood in Amman, the capital of Jordan, in the climatic zone of lowlands. Here are some specifications of the residential building. I've chosen the residential building type residential apartment because 83% of the residential buildings in Amman are residential apartments. More specifications, we can see the real footage of the residential apartment that I've chosen and the simulated one. I've simulated the residential apartment 2 times, one with its current layering of the materials and one with adding the PCMMI layer, which means that there are 2 simulations of the same residential apartment just to compare it, because this is a comparative methodology. More specifications that this is an apartment for a family of 5. Starting with my first stage was which is a numerical simulation to calculate the thermal performance of the materials. We can see that the first stage is a numerical simulation. What is a numerical simulation? Is that I simulated the residential building that I've said before, once with its current materials, without the PCMMI, the layering of the envelope is as it is now, and one with adding the layer of PCMMI into the envelope of the roof, the ground floor slab, and the exterior walls. Stage 1, which is to calculating the thermal performance of the materials. How would I calculate the thermal performance of the material? That is by measuring what is called the U value, which is the thermal transmittance. Thermal transmittance could be calculated by knowing its equation, which is W equals 1 over R, 1 over the resistance. In a very simple manner, the thermal performance, the lower the U value, this stage mainly depends on measuring the U value, which is the thermal transmittance. As I said before, that in a very general manner, that the lower the U value, the better the thermal performance there is. So what does the U value depend on? It depends on the thickness of each material and its conductivity, which means throughout this methodology, I will be parting it into 2 parts. The first part, in this stage, is illustrating and doing a simulation of the residential building with its current materials and knowing each material of the envelope with its thickness and conductivity to calculate the U value. Then doing the same everything with adding the PCWMI. Now calculating the U value without the PCWMI, which means the current situation of the residential apartments, starting out with the residential with the envelope, which is the walls. I illustrated its thickness and the conductivity. The ground floor slab, I illustrated its thickness and conductivity in addition to the roof. Now I calculated or after that the results of the U value of the current situation. I calculated that the U value was 0.75 per watt per meter square Kelvin. How would I know if this is a good indicator or not? I compared it with the codes. There's a maximum code here in Jordan that it shouldn't exceed it or be over it, which is 0.57 for the walls. And it did exceed it, which means that the thermal performance of the wall in its current situation isn't good. I've done the same thing to the ground floor slab, stating out that the ground floor slab had the U value of 1.6 and it shouldn't be more than 1.2. The roof, it shouldn't be more than 0.55, but it exceeded it and it was 1.88, the U value. Now the second part of the stage, which was illustrating the residential apartment with adding the layer of the PCWMI. I situated the PCWMI as the references told me how to, which is the literature that I read, by doing and I situated by knowing that the thickness of the rolls wouldn't be more than 10 millimeters or 1 centimeter. Here is an illustration of the wall with PCWMI, the ground floor slab with PCWMI, and the roof with PCWMI. The U value, the result of the U value here showed that it shouldn't be more than 0.55 and it was 0.54, which means it's even better than the codes with adding PCWMI, the walls. Now in the ground floor slab, the U value got decreased to 1.18 and it shouldn't be more than 1.2, which is check the thermal performance, it's good. And the roof as well did achieve a very good thermal performance by calculating the U value 0.53 shouldn't exceed the 0.55 watts per meter square Kelvin. Which means that this stage the point that I achieved was the objective because I illustrated and I simulated the residential building and compared it, and it answered the question and confirmed the hypothesis that PCWI will enhance the thermal performance as the numbers showed. Yeah, it did. Second stage is a parametric analysis to calculate the time lag of the material in the components of the residential envelope. How would I be calculating the time lag? Because time lag, as we all know, it's something that couldn't be calculated without measuring it on real life. So what I did is that I simulated it and added parameters by a parametric analysis to it. What is time lag? Time lag is the amount of time that the residential envelope will resist the exterior temperature to enter the interior or vice versa, the interior temperature to exceed to the outdoors, which means that the more the time lag, the better. So I've done this parameters or parametric analysis by doing these parameters, putting all the variables that I studied throughout this software, knowing the albedo and the reflection, the setbacks, the materials, the surroundings, the vegetation, everything in the climatic area in order to calculate the specific time lag, and by putting sensors on each 4 millimeters square, I put one sensor in order to understand the time lag and to calculate it in a very good way. So the time lag was in the current value was an average of 6 hours, while adding PCWI, it enhanced it to 8 hours by 2 hours of time lag, which is something really good. Throughout this stage, I have achieved my objective and answered the second and confirmed the hypothesis that it will enhance my thermal performance as it did. My conclusions and recommendations here that the adding double MI will enhance the thermal performance as calculated by the U value, while without adding the double MI, the envelope didn't exceed anything as the code told us to, which means it's, the situation of the thermal performance isn't as good. It's not even good. While adding the double MI, it exceeded the code and it was perfect for it. My contribution of the study was that using the results of this research, architects and designers will be able to determine the impact of reducing energy demand, and they will also be provided by numerical and computerized methods suggested for simulating residential buildings, such as the numerical simulation and my parametric analysis, because it's the software that I've done. The limitations of my study that there were no studies found in Jordan that studied PCW MI, obtaining some important information from MEMR and other situated stuff. All of those were limitations for me. Some open questions for future studies. How would PCWI react if the thickness of it was more or less? How would PCWI perform? Would it perform as good in the other two climatic zones? Because I chose the lowland, there's desert or Badia lands, and the highlands. Would a PCWI perform better being positioned next to the exterior rather than next to the interior? Recommendations using other types of PCWI. I would recommend to use other types such as the metallic alloys and study it with the mycelium or without it. Using the salt hydrates, which is my type of PCWI that I chose here in Jordan, that we can find it in the Dead Sea. It achieves very good results, and I do recommend using it in real life. And future studies should evaluate the PCWI with different material layering it in different ways than I